Well, I think we'll go ahead and get started. I want to welcome everybody to our June Sol Speaker Series. I can't believe this is our sixth one this year. And I'm Captain Barb Barton. I'm the new director of Sciences Auxiliary and very excited for that. And we have Matthew on the call, who's deputy director. Um, Congratulations to you on that, Matthew. And Yolanda, who is our Chief of Education. And also, Cheryl is our Chief of Communications. So you get to meet some of the staff members today. Um, I'm very excited that Salem has joined us today. And is from Florida. Thanks
Oh,
for joining us. um, Salem came from a recommendation by Aaron Poole. She said he was a great speaker, and so I couldn't wait to invite him to come and talk with us. Um,
oh, thank you.
he's a NASA Jet Propulsion Lab Solar System Ambassador and honorary admiral tonight.
Oh, thank you. Thank you so
Give
much.
you the honorary title of admiral. He's known for delivering engaging public talks, and that's confirmed by Aaron, covering the latest NASA missions and updates. Um, you've got a leading position at a dynamic semiconductor company. Um, you're an engineer, I'm assuming,
Yeah.
and work in AI, signal processing, digital imaging, astronomy, and physics. But the best thing is that you share the wonder of the cosmos and the intricacies of engineering with both science enthusiasts, the broader public, and Starfleet. So thank you and welcome to the Sol Speaker Series.
Thank you. Thanks for inviting me. So I'm excited today to basically give you some highlights and some updates. Okay, and yeah, just let me know when I can start, and I will start. Okay, so thanks very much for inviting me for this talk. So my name is Salem Emara. I'm NASA GBL Solar System Ambassador. So what is that? Is volunteer organizations belong to GBL, and main motivations behind the team are actually to organize science talks or like science events with the general public to educate um, um, the general public basically about what is NASA is doing. And in today's talk, I have almost 30 slides. Hopefully, I can finish go through them in 45 minutes, so we can leave a room um, for questions. So I think actually today I choose typically like when I make a talks like this one. Um, I basically pick one of the mission and go a little bit in details about what's happening, what is the latest results, and that basically is what I typically do. But for today's talk, actually, I did something slightly different. I said, okay, maybe actually I do something slightly different because there is so many very interesting missions, groundbreaking, like very interesting missions actually available. It is to be launched, or basically already we are receiving results out of it. And I want to put the story together. I want to basically make sure that is okay what we are doing and how why we choose to do it this way, not the other way. So I want to basically have highlights about what's happening. Okay, about what? About searching for life. So this topic is a topic we ask these questions for thousands of years. As long as we have a history written, actually, we are having these questions answered. So today, actually, I want to achieve a goal that is okay in go through this in slight detail. What we are doing today. to answer these questions, because maybe we are the lucky few that is we're gonna witness in the history in the history of a human being. We're gonna witness a breakthrough answer. And why I believe actually this is we are very close to answer these questions. Right? So for uh, as I mentioned, actually for thousands of years, we pretty much um, asking the same questions. And but the only tools we do have to answer this question is our eyes. So for thousands of years, our ancient ancestors, they have only the eyes. But it's very interesting. The carefully they look into the sky, they learn more about the sky. So they have nothing. They don't have instruments we do have today. We don't have telescopes, but they have the eyes. When they look into the eyes, they observe. They have some observations, and based on these observations, they notice actually there is a pattern in the sky. When it happens, the cold season will come, or like I can basically start my growing my crops. Or so they found that there's correlations between the stars or like the sky patterns and what they do in Earth. But they have the questions actually, are we alone on this? Okay, like, but for them, the whole universe is basically is Earth, and basically what they do is just basically all what they have their eyes. Until Galileo, at one point of time, they basically look into the sky with his with telescope, and it's we know like for all these thousands of years of observations, that is basically completely has changed. And now they basically prove that is okay. We are not the center of universe as our ancestors, but he confirmed, of course, like Copernicus actually was the first one basically predict that is okay, Earth is not the center, but Sun is basically the center of our universe. But Galileo, when he basically looked with the telescope, what he found, he confirmed. And how does he know that? Actually through the shades, actually, or the shadows of thermals. So it's very interesting. Anytime we look to the sky with a new capabilities, we discover something. It changed everything we know about ourselves. And this pattern continue over and over and over. Like for example, when 500 years after, when we have much bigger telescopes, okay, Erwin Hubble, he basically looked into the sky, and he changed everything about we know about the sky, about ourselves. Because why? Because in our is not far from where we are. In our grandparents, okay, in their books, our grandparents, we're not talking about hundreds of years. We're talking about a people we may contact them at one point of time. Okay, that is the whole universe was the Milky Way. For them, the whole universe is a Milky Way. So basically, they believe, of course, like now, actually, they have better telescopes and they look into the sky. But for them, the whole entire universe is a Milky Way, is one galaxy. But when Erwin Hubble actually has much bigger telescope, better capabilities, what happened? We changed everything we know about. Still, we have a breakthrough. Every dot he see in his very deep like very sensitive instruments, every dot was another galaxy. They discovered that is a breakthrough that is not only we basically we changed the view of the sky, because every dot in his photos actually it turned out actually it is another galaxy. So that basically was a breakthrough in our how we look into the. So the questions actually, okay, this cannot be basically, this is the universe is so huge, it's so vast, and cannot be basically we are the only people actually living in this huge, massive universe. We have we have thousands, so like hundreds of billions of galaxies, not stars. Like in our Milky Way alone, is hundreds of billions of stars. So that basically is mind-boggling. Like, and we cannot basically be alone. So before basically like see what happening today to answer this question, I think actually we need to agree. Okay, let us basically agree what is life, because we keep hearing actually NASA's searching for life. The European Space Agent is looking for life. So, but actually, let us define what is life. Of course, like you can Google what is life. You can like Webster dictionaries. You're gonna give you very interesting, complicated definitions of what is life. But you can basically simplify that, and you say, okay, I have a much simpler versions than the versions from a Webster dictionary. No, of course, no one is using dictionaries any day these days. Okay, everyone using the autocorrections. Okay, so but anyhow, if you get a chance, you can go online and basically type what is life, and you get a definition. But the summary of what is life, anything actually, any object, whatever it is, can eat, can grow, can respond to surroundings, and make new copies of itself. So that is basically my simplified versions of what is life. But that is exactly the definitions you can go to any dictionary or like some biology class or something. Okay, and basically you can map it into whatever I'm writing here. Okay, so let us make a test for ourselves. Um, for example, how about microbes or bacteria? Okay, does it eat? Yes. It can take some organic components, and can it grow? Yes. Can reproduce? Of course. Like it's like can it respond to external? Yes. So we know that is microbials are is a living thing. It's alive. Okay, it's a form of life. How about a car, for example? Can a car um, can a car basically identify as a life subject? Does it eat? Someone will argue, yeah, that basically we put some hydrocarbons, like some form of food inside the car. Okay, does it grow? It doesn't. Does it respond to interactions of course, like we basically cars actually nowadays, in Tesla car for example, actually like it's a see pedestrian crossing, it will stop, or like if it see like a red signals actually, or like a red traffic signal will stop. So basically it has some response to external surroundings. Okay, can it reproduce? No. So is it alive? We cannot say it is alive, right? How about a cat? Of course, cat can eat, can grow, respond, and reproduce. So it is a form of life. But this form of life, we have to basically give it. It is not like a bacteria form of life. It is intelligent life. How? Why we label it? Because it can solve the problems. If it is basically looking for food, it will go and look for the food. It can solve some form of problems, and when it does that, so has some form of intelligence. So a cat, animals, snake, or whatever, lizards, okay, those actually are not, it has some form of intelligence to interact with the surroundings. How about human? Human also can do everything, okay, of course, but human is a special class of life, which we call it super intelligent, right? So we are super intelligent more than the cat. Okay, at least what's how this is how we believe, or at least that's what we believe. Okay, so that's good. How about ghosts or like spirits or like something, correct? And does it eat? We don't know. Does it grow? We don't know. How it respond to? We don't know. Does it reproduce? We don't know. in matter of fact, actually, is it alive? It is a silly question to answer, to even investigate. Why? Because we talking here science. We are not talking about metaphysics. Okay, what is science? Okay, science actually defined by great philosophers in the Renaissance, correct? In the in the 1600 eras, correct? We basically sit together and say, okay, we cannot basically mix and match between ideas and mythology, and let us agree on a common ground that basically anything we can test and measure a way all of us agree on it, okay? Then, and also can be tested, and if we test it, we have to agree on the results. So science is about testability. Science is about um, um, a common agreements. Okay, even actually, for example, actually, when the people actually like those ancients actually when they believe actually the Earth is the center of the universe, and they have this problem of what's called the epicircle, correct? Like because actually they see the planets in the sky wandering around, and basically it's not doesn't have the pattern they see with the other stars, correct? So they come out with a theory, and a very accurate theory to predict where is Jupiter's, where is Saturn's, where is Mars. How can basically you can calculate it? In matter of fact, it's very complex math actually to do that, but it is a good science, correct? Why? Because it is testable. I can write you an equation or like a model, and I can predict where is Mars will be. But the problem actually will happen when the model is shifting here and there, and you keep basically for thousands of years, they basically try to tune up this model way or another. So when they do that, they try to basically be as close as to. So it was a wrong view to to the universe, but was a correct model, a correct science. Okay, they were not wrong until we have a new discovery. Our new discoveries was 100% much more precise and much more predictable than the old model. It's just basically gives us more precision. So this is basically science. So the questions about is spirits or like ghosts actually they are it is basically it's not really actually it's a science. So now basically we have a common definitions what is life, all right? And we saw that is this form of life either like it is intelligent life, super intelligent, or some form of primitive life like bacteria, because each one of those has a different technique to go and look for them. And we're going to see basically where we are actually in the common current missions available today, what we are doing to differentiate, to look for what type of those life patterns. Okay, but how, where we go and look for life? Of course, like we can look for life on Earth, in our solar system, in the Milky Way, and cosmos, right? So this is basically. So of course, like looking for life in Earth is much easier than you travel somewhere. But definitely going to the solar system, studying the solar system, life in solar system is much easier than you look for life in the Milky Way. And we'll see the challenges and what we do to basically overcome some of the challenges. And of course, look for the life actually in the broad, basically everywhere in the universe. Okay, but the only life we know about, that is the only life until this talk, actually, the only life we know where? It is in Earth. So if we're gonna basically go and look for life, we need basically look for life we know, correct? There's another form, actually, a matter of fact, there is a lot of scientists, they they don't basically limit their views about life, the way actually we live here in Earth, or like the life patterns in Earth, but they look for abroad. Actually, maybe there is some other form of life we don't know about. But if something we don't know yet, so it is, yeah, we can investigate it, but the only life pattern we know today is what? Life on Earth. Okay, so if we're gonna go, so the question, the simple, if we need to go and look for life, let us basically look for a life we know, right? So what we know from the life on Earth, we know few things, correct? One of the most important things we know are life cannot be in the extremes, and there is a reason, by the way, and I can basically go through the details why is there is life cannot be in the extremes, the huge extremes. Okay, like let's just say that. Okay, and I can answer these questions if you want, but here in Earth, we don't see life in the magma of volcanoes, for example. Like you take a piece of volcanoes and you go basically, does any things living here in this in the like the melting rocks? We don't see it. How about actually we go to like the South Pole, and we can look for life in the South Pole? There is not varieties so too much. Like life is almost rare. There is no trees. There is no flowers. There is only penguins actually downs actually by the beach. But actually, when you go to that, um, there is not huge form of lives. Actually, so it sounds like life uh, for way or another, like in the moderate, right? So if I basically model, go look for a life in some other way, other planets, or like some other places, I should basically look for similar conditions, right? And that basically is a very important criteria, and we'll see how and why. Another interesting, okay, patterns of life on Earth is we know, understand that is okay. Life love water, and whenever there is water, whenever there is life. The more the water, actually, there is more life. The varieties actually, and fresh water, the availability of fresh waters and rains, it basically reproduce a lot of very diverse life, creatures actually live in this, or like even planets, you know. So it looks like life, it depends on water. That's why when we say, okay, like how we look for life in somewhere else, we look for water. That is fundamental. Okay. What else we know about the life in Earth? We very interesting. Life on Earth has its own signatures. Like how, for example, actually there is methane on the Earth's atmosphere. Methane is very interesting molecules to look for. And why is that? Because methane is, it breaks basically by the sun rays, correct? Like it breaks. Correct? It doesn't basically, it's not a stable, it just basically it oxidizes, and basically it doesn't stay for long. So if there is no source of methane, regenerating methanes, okay, theoretically, after thousands of years, or like it depends on the size of planets and stuff, we should not see methanes. So methane is something like, if we detect a methane, basically means that there is something is generating this methane, and this is very interesting point as well. And um, and so, for example, so why it's so interesting, the methane? Because methane actually exists actually in, you know, um, mammals, for example, they eat and they produce methane. Cows, for example, produce a lot of methane. And matter of fact, actually, part of um, um, methane detected on Earth, mainly actually from living animals. Okay, so there is many molecules like methane, like ammonia, for example, and there is so many others. Those actually are molecules. It is indications for life. And those actually, we call them actually the biosignatures. Okay, you're gonna hear this term through the talks quite a bit, correct? The biosignatures. Okay, so what we know so far, we know that is okay. If we're gonna go look for life, we need to look for biosignatures because we know the life, the form of life we are, we found it on Earth, a rocky planets. So let us look for rocky planets, and it has to be in not in extreme temperature, not so super cold and not super hot. For, like for example, so this basically if the planet with it is in a good zone, that is it is not very close to the sun, to the star, or is not far from the star. In a there is a sweet spot, and this we call it habitable zone because I'm also like this actually I'm gonna basically refer to this term all the time. Habitable zone like means that is okay, I can in this that is basically is a good temperature range for this planet for life to survive. If the star if basically Earth actually is so close to the sun, there is no life actually because everything will be melting and very super hot thousands of degree, and at least the life we know is not gonna be exist. And if it is very 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 cold, because sounds like life needs the energy coming from this heat from the stars, and that is how it survives. um, Also, like we need to look for water and we need to look for biosignatures. So this is the four criteria when I go and look for life. That is basically the criteria I'm looking for. I need to look for rocky planets. It has to be habitable zones. It has to have water. It has to have biosignatures. And you see, in this talk, all the missions I'm going to refer to is just basically try to find one of those criteria. Okay, so let us see how we can basically look for rocky planets. We need to look for rocky planets. How can we do that? The most like the most important technique used today, there's so many techniques, right? But there is two main techniques, or maybe three techniques actually, but very common to find planets. And the most famous one so far, or successful ones so far to find planets, is we call it the transients. What does this mean? Means that is okay, if we have a sensitive telescope with a camera, sensitive camera, that it looks into the star and it see a dip in the star brightness because the planet go in front of between us and the star. When the planet go in front, there is a dip in the brightness. When I detect this dip in brightness, the dip, I think basically we conclude that is okay, we found a planet. So that basically is, we call it the transient technique. There is so many other techniques, like there is, we can detect when a planet, for example, uh, orbits a star, and actually both of them actually is basically wobble, correct? Like because actually they have, there's, I don't want to basically be too technical here, but the star, it's actually even actually our sun, because Jupiter is so heavy, it is the sun is almost shaky because of the Jupiter orbiting the sun. And when you do that, you can basically detect the variations of the spectrum coming from the sun, and you can see, oh, there is, or from the stars, and you can see this variation. If you can detect those variations, you can detect, you say, okay, oh, there is a planet here, right? And of course, like direct observations to the planets actually is a technique, but it has its own challenges. Hopefully, maybe I can highlight actually what is like the challenges actually to observe planet directly. So that basically is the most common technique today used um, uh, to um, uh, to detect planets. How we know it is rocky or not rocky, correct? I think it's very easy to do that even with this technique, because why? You can estimate the the mass of the star, okay, based on like orbit times, and you can basically know how basically you can come out actually with the techniques. You can um, estimate the mass of the sun of the planet, and also you can estimate its size, like its volume, and from the size and the volume and the mass, from the volume and the mass, you can do the density. And when you know the density, you can know basically if it is a rocky planet or non-rocky planet. And this is basically how we do that. Okay. Remember, in my lifetime, okay, I'm talking about myself. In my lifetime, when I was young, there was no talks whatsoever about planets. That is something completely recently, in the last 20 years. Okay, there is no literatures beyond before 80s, in 1980s. Okay, talking about planets. Actually, this science doesn't exist. That is brand new science. The first confirmed planets existence, actually, of course, like we don't have at this time, we don't have missions to do this type of work. So there was basically ground scopes to find like some form of transit, but was not confirmed until like it took so many years actually until they confirm it. It was basically only in the 90s. Then we need to basically go do much better job. Okay, so what we did this Kepler telescope, right? So Kepler is um, a space telescope that is found so far more than 2,500 confirmed planets, and means that is okay. And some of them, of course, like this actually, like it start basically from, we switch from we don't know any planets to an era that is we know about one or two planets outside our solar system, correct, into an era with basically thousands and thousands of planets. Kepler, by the way, is look into one very small spot on the sky. Okay, almost like if you extend your hand, it is the size of the palm of your hand, correct? Like you just basically it looks into the very very small area of the sky, and keep looking in the same area for years and years, and waiting for this depth to happen in the spectrum, in the light, received light. And so far, it was so successful mission, to a degree that it is basically they extended so much. Matter of fact, they have Kepler 1, that is the first original one, and they have another missions they extended to become Kepler 2. Even actually, it is broken at the Kepler 2, but still actually even actually it is was one of the um, like one of the like gyros actually broke, and basically cannot aim to the same area over and over again. So, but actually, they have 6 months. I have to go to the direction. 6 months to the other direction. Questions? Any question? No.
Space.
I'm sorry. Actually, I didn't hear the question. Is any question or?
I actually have a question. It says
Sure.
3.12 gallons of gas used.
Yeah, it's just I think actually because typically um, um, spacecrafts to need some fuel to basically orient itself, basically adjust the basically adjust its positions. It has to be some corrections every once in a while, correct? So we don't need this much actually in space. We don't need much of um, um, it's just basically small nozzles. Actually, it produce a very tiny burst of basically. So basically, a tank of fuel can basically stay for tens of years, like for so many years, because we don't need so much actually in space, correct? It's just basically like to do some orbit corrections and orientations, right? And it depends on the mission.
Sense. I just wish I only needed 3 gallons of gas in 9
Me
years.
too. I switched to electric, and I'm so happy I did this decision, by the way. Um, so um, so that basically was a Kepler mission, right? So it looked into one um, one locations over and over. So basically, like in this part of the sky, million observed stars. By the way, actually, just a reminder here, when you go to the night sky and you look into the stars in the sky, those actually, as like all the stars you see here, you see with your naked eye, are stars in our Milky Way, of course, and they are very close to Earth. All of them, they are very, very close to Earth, right? This is the skies actually we saw with our eyes at night. Okay, but so it was basically very successful mission. So na- like NASA basically we launched actually the um, another mission, and which we call it TESS. So Kepler basically stopped operating in 2018, so almost like 6 years ago. Then immediately they launch another mission, which is basically currently still operating, producing phenomenal results. It's called TESS. So TESS basically much like the part of the sky it look at, it is much bigger than it's much bigger than whatever Kepler was looking at, right? But what we basically need to do is just it is some what's called this mission we call it surveyor, correct? We need to look for the whole entire sky, and instead of one spot in the sky, let us look for the whole entire sky. So how we do that? We just basically look for much bigger area, like the field of view. It will be bigger, and I need basically to like move from one spot to the other every month. So every month I go in this, like remember Kepler for many years looking into one spot in the sky, but this mission is completely different. It's basically it change where it looks every month. So every month basically look into different areas of sky, and because we don't like but what happened, we look into much bigger area, so hopefully we can capture have a chance, increase the probability to find planets doing this way. So It is the by the way, actually, the major difference between Kepler and TESS, which is currently operating in the sky. TESS basically orbits the Earth is in 14 days. It's like, for example, Hubble Space Telescope. Do you know basically how long actually to take? Anyone knows this? Answer this question. It is how long Hubble orbits the Earth. Ob Hubble take 1.5 hours to orbit Earth. Like Hubble Space Telescope. I hope actually everyone knows about Hubble. So it took 1.5 years to make one orbit in the sky. How about Kepler? Kepler was basically is not orbiting Earth. It was orbiting the sun. It is basically follow in an orbit following the Earth, right? Because we're trying to avoid the problem with Hubble, because Hubble every 1.5 hour, like it do observation for 1 hour, then they have to shut down the telescope because basically it is in the shadow of the Earth. It basically, so it keep basically doing this. So every 1.5 hour is very complex to operate, right? That is the problem with. So for this type of missions, that is, we need to look into the sky for very long. We better go do something else. So Kepler, they solve this problem by they have an orbit around the sun and it basically follow Earth. In tests, actually, they said, okay, this is completely different. They basically make an orbit that is 14 days. It goes actually beyond almost the moon and come back. Okay, so we can basically focus the telescope on one spot eh, for at least 1 month. One orbit actually 14 days. So every 28 days they change the like the aim of the scope of the telescope. Right. So far, how many confirmed planets actually coming from these missions? It's like 400, but there is thousands, okay, of other candidates. I think actually the last I hear, every time you refresh the web page, actually, when like this number actually could change, but something in the neighborhood of thousands. Like I think actually the latest I read actually was something like 17,000 or something like that. But because it's not like Kepler, which is um, um, it's not like Kepler, which you look into one piece of the sky. It is it will mainly will collect data from a very near stars, like in the range of 300 light year away from most of the planets we're gonna find in this range, like the range of um, 300 light years. That's how far it is. 30 to, this is the sweet spot, 30 to 300 light year away from Earth. Okay. So that basically was what was um, uh, 10 years ago to and the current, which is this. So what about the future? So in the future, there is another interesting missions. We call it, it will be launched in 2 years from now, 2026. That basically also like do some form of surveys, but it is not designed to survey planet per se, but it has capability to look for uh, planets. And I can basically answer questions about this mission because it's very interesting, maybe later. But that is basically is the next, right? It has we can look or observe far away planets from its stars using the Nancy Roman space telescope, which is coming, as I mentioned, it is in 2 years, should be basically be launched. And by the way, actually, like here, actually, to say basically the benefit, because For example, Hubble Space Telescope. Hubble Space Telescope is a telescope, is not a surveyor. But those missions I mentioned, which is Raman Space Telescope, Kepler, TESS, those actually serve like are almost like a surveyor. It look into very big portion of the sky at once, right? So, for example, actually, for Hubble to make one image by Nancy Roman, for example, one image from Nancy Roman will take Hubble to look into the same part of the sky. Maybe Hubble need 100 years to do that. But because why? Because it has huge field of view. Like the area it looks into the sky actually much huge. Of course, the sensitivity of Hubble will be it's basically because it look like it focus on smaller areas, and for a long time it can basically do look into very faint objects. Nancy Roman actually has the same capability because it has the same mirror dimensions used by Hubble, like a 2.5 meter range. Okay, so now actually we answered the first question, or I hope actually I answered the first questions, how we look for rocky stars, rocky planets, right? I saw you, that is okay. We have already 3 missions. Two already, one is done, one is currently operating, and there is one one in the futures, near futures, okay, which is Roman. And there is another one actually European Euclid, but actually Roman and Euclid, they has a different also like operation, not only different science mission, which is basically studies dark energy, but I'm not gonna basically go through that. Okay, at least for this talk. Okay. So hopefully I answered the first part, how we look for rocky planets, or how we look for planets actually outside our solar system. So another basically very interesting things actually about life on Earth, on how the life on Earth started. What we know from so far about our own Earth, first of all, actually we know that is okay, our Earth is around formed some maybe 100 year or 100 million year after the sun or something. So basically we assume the Earth actually it is 4.6 billion years old, right? That is basically the current assumptions or good assumptions. Okay. And but there is no way on Earth you can find any rock from this era. There is no, like we cannot find specimens on Earth, okay, older than 3.9 billion years, around 3.9 billion years. And this was very, like almost like someone erased from the Earth's history 600 million years, almost, or like even more. So all the history of Earth is almost wiped out. And how we confirm that? We confirm that because we went to the moon and there is, I don't want to basically go through this details, but if you have questions, I can basically answer. But you need to believe scientists actually in that, correct? It's like the history of Earth, someone wiped the history of Earth. But interesting enough, we know that is okay. So why is that? Because we believe actually Earth basically was started as a lava, a melting rocks, then it cooled down, and somehow it melt again, and we understand the mechanism, correct, why it melt again, and we call this late heavy bombardment. And we believe actually there's something hits the Earth and basically it melts the Earth completely. So interesting. That's why to answer the question basically how the life actually started at Earth. But recently, only recently, like maybe 10 years ago or something, less than 10 years ago, maybe, or maybe, yeah, less than 8 years ago or something like that, they discovered that is okay, one of the oldest specimen of rocks they can found, and that basically a very special type of rocks, um, um, you know, and that basically we call it stromatolite. And for example, actually, the picture actually in the on the right hand side in the down is this basically I took it personally in the Houston Science Museum. I was visiting there and took this picture because it shows this specimen very well. So, but the specimens actually they found actually stromatolite actually it's very interesting rocks. Why? Because it is we know that is actually these rocks actually it is a rocks um, the shape of these rocks or like the layers in these rocks it is basically has to be done it's because this process exists today like for example one of the pictures I have here actually in here it is those actually living organisms can basically cause this layering in the rocks okay so we know that is when we see these rocks we know that is at this time there was some life form of life okay even it is primitive form of life then we found like a very one is 3.7 billion years old rock correct so we know that is confirmed that is okay there is some rocks life in this time in this era correct as old as that but remember I told you that is you cannot find a rock older than 3.9 on earth there is no such thing you cannot find that right but you can find an older than that basically piece of like a sands maybe you can find those and when they analyze those pieces of sands they found that there's some carbons okay materials and it shows that is okay the ratio between the two carbon 12 13 it indicates actually there was a life actually at also like at this time so this is very interesting now correct it shows that is okay 3.7 years it could confirm there was a life on earth and even before the melt because we have this grains of sands basically it's not grain of sands it's zirconium like a material like some form of oxides actually and some form of like you know so it shows this specimens it shows that it was alive so this is very interesting here because it shows that is okay anytime earth cool down and there is a water immediately life started on earth that's very interesting okay so that leaves us actually with two possibility for how life started on earth one theory we call it we will call it panspermia panspermia means that is okay maybe because someone has to answer this question why immediately the moment earth has water it has immediately it has life so there's two theory either like life come from the space we call this theory panspermia means that is okay maybe actually life this is actually so commonly available on the universe and somehow basically some asteroid hit earth or something like that and immediately the life started um, on earth but another theory is called what it's called biogenesis biogenesis what is that that basically sometimes actually you go to very extreme spots actually in earth and you can find some form of microbial life so means that is okay the life started from the earth with itself it doesn't come from space but how can basically answer this question? There is no way you can answer these questions by sitting on Earth. One of the one An easy way to basically answer this question is we can go to somewhere else and look for life on something somewhere else, and that's exactly what we do. So we go to Mars, and start to look for uh, um, you know life, or like an ancient form of life on Mars, because Mars actually become actually very interesting planets basically to look for life on. But because we need samples, like there is no way you can send to another star, to basically another nearest planet. The nearest planet actually will be, I mean, outside our solar system will be impossible to go. Correct? Like 2.5 year, like a four and a half year, a light year, correct, away. So this basically there's no mechanism we know of we can visit any other close by star system. So, but we can go, and it's easier to go to visit Mars, right? And why we like Mars? Because we found traces of methane. You remember, actually, I told you that it's okay. There is methane, and like it's not a stable molecules, and it will break if there is. It has to be regenerative, right? And also, actually, I'll come back to this story because now actually it changed. Like the recent up-to-date studies shows that is okay. Maybe actually we don't detect this much methane actually in Mars than with what we thought originally. We do see that is okay. There is interest evidence about the water on Mars, and there is also like there is an ice under the surface of Mars. By the way, when say NASA is looking for water, water basically is very. Let me just explain something here. If someone from a different universe come to our universe and look into our universe, what he will see? He will not see anything. He will see only hydrogen and helium. 99% of our universe is hydrogen and helium. What is the third abandoned elements in the universe? Anyone knows? It's oxygen. What does mean? The highest element on the universe, 75% of our universe. I'm not talking about our solar system. I'm talking about the universe, correct? 75% um, is is hydrogen. 25% is helium, and there is everything else is 1%, and half of this 1% is basically what is oxygen. So the highest abundant elements on the universe is hydrogen. The second one, helium. The third one is oxygen. So what is the most common molecules you should expect on the universe? It's H2O, the water. Water is everywhere. But we are not looking for ice water because we ice everywhere. We know ice everywhere. Water everywhere. In our solar system, in our universe, H2O is very abundant. What we're looking for are traces of liquid water because we know life, the form of life, okay, we are basically belong to, is like to have an liquid water. So one of like if you see in the upper right corner of this is basically like between it's a two picture beside each other, one for in Mars and one for Mars and one from Earth, and you can see that how they exactly looks as each other. And that's basically very interesting. It shows that is okay. Mars at one point it has liquid water, right? And there is very interesting also like spots, okay, in Mars. You can see there is a delta. Okay, I'm not sure if you can see my mouse moving or I'm not sure. Do you see my mouse? Maybe
No.
no. Hmm, interesting.
Wait, I think I might have seen. Yes, there
Oh,
it is.
okay. Okay. See. Okay. So you can see there is a delta in here. You can see there is very interesting. So this is a spot. It's called G0 craters in Mars, and you can see there is very interesting. And scientists actually believe it used to be a lake, okay, and there is a flowing of water, and this is river delta being formed, that is basically this area. Um, so that basically is the idea. So what we have to do now, we have to go to this spot and bring some samples from this spot back to Earth. And did we do that? Yes, we do. Yes, we try to do. What we have today is a mission still operating. There's both actually of them actually still operating, Curiosity and Perseverance. So Perseverance is visiting the Jezero crater, and it is basically around the delta I just basically showed to you in the previous slides. And what it's doing, it do a very interesting sample collections and very interesting chemical analysis to the rocks in these areas. Because if there is a life, if we want to answer the questions, are we the life in Earth is a form of um, a biogenesis or some other or like basically it is the life is basically everywhere. If the life is everywhere, we should basically see it in. If there is a spot we can find a life on other planets, this is the spot we should be, correct? Because it has very strong evidence that there is a flowing water at one point of time, and we should basically see some some form of rocks creations, that is we can analyze it and we see, oh, there is some like there is some traces of carbon hydrogens and molecules that is basically can foster life at one point of time, or there is can find traces of life started at this. So this is basically if one of the most exciting missions I see, it is basically this Perseverance, because Perseverance going to one of the most leading edge or the spots in our solar system to can find this form of primitive life. But of course, like it collects the samples, put it in a tubes, but it leave it in place. So there is a missions will be hopefully will be launched in 2020 like 2027 2028. So we'll basically bring this sample back to Earth. And basically there is so many now actually already it is in the plan, like sample return missions. So there is two mission. One basically will be an orbiter and one will be a lander. So the lander will land and collect the samples from Perseverance and basically go and basically launch itself. It doesn't have too much fuel, so it will launch to itself actually to the orbiter, and the orbiter will collect those samples, bring back them to Earth. And there's a lot of talks actually, how can we treat those samples? People, the they have to be careful with this. Anytime actually bring something from Earth, from space to Earth, you have to be very careful, right? Remember actually in COVID, literally the whole Earth actually was shut down. Do you know how much materials COVID actually, if you basically collect all the virus in the Earth and put it in a container, how big this container would be? It will be a spoon. Like it will be like less than a spoon. So it takes the whole Earth basically shut down because material less than a spoon, like a teaspoon, right? Or sugar, like it's basically like you can think the whole entire viruses. If you collect all of them, you can basically put them in a little. So I think when they bring anything from space, actually they have to be very careful in how to study it, how to contain it, have to make sure that there is no leaks and stuff like that. But I'm not personally, I'm not concerned about it. We have so many rocks actually in Earth actually coming from Mars. It's confirmed. So we get visited by Mars so many times. Okay, a lot actually. In matter of fact, there is a lot of you know, species from Mars already on Earth. So okay, where else actually we can look for? We can look for there is very interesting, um, very interesting other moons. Okay, in our solar system, one Europa, and it's one of Jupiter moons, correct? And that basically is confirmed to become. It's basically an icy. It has a thick ice shield, and we know if there is a ice, there is under the ice there is will be a water, right? So maybe actually there is a fish actually under this glacier, under this ice shield. So it's a very interesting spots actually to go look for life as well. So what we're gonna do, we have mission to go to Europa, and there is one actually hopefully will arrive. It will be launched this year, and hopefully it takes like to arrive there. It takes 6 years. So hopefully by or like maybe around like 5 years, five and a half years. So it it will basically hopefully by 2030 will arrive around Europa and spend time basically do analysis, and will be a follow-up missions to go and try to dig in the ice. But we have to be very careful, because if there is a life, you don't want to basically introduce your own life first of all, and also like you don't want to disturb. If there is a possibility there is a life, if there's a fish living inside under this ice cap or something, you don't want to basically disturb it in a way that is okay contaminated. So they have to be. So there is a lot of plans today on how, and there is a lot of proposals on how basically to achieve this mission, to go to um, um, you know those type of moons and dig underneath the ice. Okay, so now I show you in very interesting how to look for rocky planets, and how can we look for a primitive form of life. We go either like to Mars, or like we plan to go to those icy rock moons of Jupiter's and Saturn. But we have a very important mission, or like a very important telescopes available in the sky today. We use them. It's called James Webb Space Telescope. So James Webb Space Telescope is very interesting telescope, because it has a capability we never have it before into space. Remember, anytime with a new capability, we look into the the sky, we discover brand new stuff, and this pattern is always there, right? So uh, James Webb Space Telescope is 6 meter telescope. Okay, and if you have any questions about James Webb, just basically ask me. I cannot basically cover much in it, but actually this is the idea. It's 6.5 meter telescope. It's much bigger than Hubble, and it has very interesting capabilities. It can do can detect biosignatures through the spectrum. So what is spectrum? Spectrum just basically takes the light coming from a star and basically put it through prism and see basically what is color components in the. But I don't use the word color because sometimes in infrared, this actually operate in the infrared, mainly in the infrared, which basically this notation of color, it doesn't exist. It just basically spectrum mean different wavelengths, right? So it's very interesting, actually, the technique actually they use to detect biosignatures materials, okay, on planets. If the planet come between us and the star, that basically we can detect it as in the transient. But if I can take this light and I can analyze it, I do the spectrum for it. I see what is the frequencies actually, or like what is the wavelengths, okay, for the I can detect, because each molecules or each compound has its own signatures and how to absorb the light. By looking into that, I can basically detect what materials in the atmosphere of this planet. And this is very interesting. This is stuff with this is like James Webb, it opened a new era, okay, of for scientists that was not there, because infrared imagery from Earth is almost impossible. Not impossible, but the capability basically like you have to go beyond our Earth by far, because what's called background radiations, like everything basically glowing in the infrared. So have an image using the infrared, it's almost like you want to take an image to the sky during the day, correct? You don't see anything actually during the day to the sky, because there's so much scatters noise actually from in the sky. You cannot see any stars. Similar with infrared, you cannot take a good because of the noise, or like because of the radiations, like heat glow actually in 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 in, in this wavelength range. So we cannot make a good infrared images to the sky from Earth. So what we do, we have what's called James Webb Space Telescope, and James Webb has like little bit of visible light, and also like but mainly in the infrared, short infrared and long infrared. Okay, so what James Webb actually tell us so far, it's basically mind-boggling. It's basically I cannot basically uh you know sit here and and explain everything. It just basically, it is amazing actually findings actually what James Webb did for us. Okay, so it is basically confirmed there is many of the planets actually we discovered that is okay, it has um atmospheric water vapors. It has some interesting chemicals, okay, like even actually bio like some basically very interesting compounds to life, important to life, available not only in the planet, it's available also like in the uh, discs actually, like plants disc actually, like around the planets. And so it's very interesting finding actually to answer this type of questions, correct? There's so much data in this field, okay? And for example, that basically, I think actually like that uh, that basically finding actually there is a very interesting actually finding from James Webb almost on a daily basis, but some of them actually take media attentions more than others. For example, this like this planet. It's called K218. I was following this finding actually for a long time. Why I like this planet? First, actually, it's in habitable zone. Second, basically, it is habitable. So basically, it's hit. It hit like it check mark is the first check mark, correct? And you can see it has methanes. Okay, and it they discovered that it has methanes, has CO2. But one of the interesting compounds actually I was get me excited is basically the DMS, correct? Dimethyl sulfide, or like the DMS, is a compound only in Earth, cannot be, there is no natural process can generate this molecule. It in Earth, it is the only way you can generate this molecule. Of course, like some maybe paper factories or something like that, correct? But actually, also like we know most of it on Earth is coming um, um, from the oceans, because actually there's some organisms actually producing this gas. So the detections of DMS actually in here is very strong indications that is okay. There is something interesting at this planet, right? And there is so many. I'm not gonna go through all the theory about like basically what is the finding in here. But if you have a questions, I can. It's very interesting planets to look at. But now actually they narrow down hydrogen ocean. It's basically hydrogen atmosphere with basically ocean underneath. That basically the leading theory about this K218 planets, which is basically I follow the news for this specific planets over and over, right? And this planet actually basically it's almost like 100, maybe I forgot, 120 light years, so it's very close actually to Earth. And it's first actually discovered by Kepler. Kepler basically is the one, like mission Kepler. Remember mission Kepler? They discovered these planets, and now James Webb actually doing analysis for this specific planet. So you can see like there is hydrocarbons in protoplanetary disks, means that is okay. It is we can find um, hydrocarbons, which is basically indicative of um, it's indicator, but it doesn't mean that it must have life, but it's one of the indicators, right? Like for example, oxygen, the availability of oxygen, it helped to tell actually maybe there is a life, but it doesn't mean that there is a life, correct? It's just basically it is a signature, correct? Okay, so now we know how to basically look for these biosignatures, okay, through this James Webb Space Telescopes and beyond. Of course, like there's so many planned, very interesting missions, future missions to look for those biosignatures. So that's basically how we look for biosignatures, how we look for primitive lives, and how we look for rocky planets. Now, how about the super intelligent life? In super intelligent, we basically have to see it has a patterns, like humans' activities. It generate a pattern. It make basically our atmosphere naturally imbalanced. There is some stuff more than others. Like there is, for example, there is a CO2 than what basically we can justify because we are burning a lot of fuel, but for example, in our atmosphere, right? When you model Earth without human activities, it should basically have less CO2, but somehow basically there is a CO2, so this imbalances, okay? So super intelligent life has its own signatures. One of the most important signatures, okay, for example, okay, is radio signals, right? Like we humans, we generate a lot of radio signals. We have TVs, radios, cell phones. Even actually, we have a very strong very strong radars for military radars, for example, right? Like this is are very, very, very strong, right? So these type of patterns, okay, if we can look for it, because actually, if we assume that is life everywhere, we should basically look for patterns. If we come out with basically a way to communicate through radio waves, we should basically the other intelligent people most probably they can achieve the same, correct? There is no why we are so special to a degree that okay, we are the only one who will discover the radio and no one else actually will discover the radio. So in the 60s, for example, actually, when people proposed this big Arecibo telescope, I'm not sure if anyone went to Puerto Rico and visited this telescope. I did before, of course, like there it's collapsed, completely collapsed, and there is no fund for this telescope, so basically no maintenance, and unfortunately a few years ago actually it collapsed. But I was lucky, actually I visited this place actually before it collapsed. So it's a huge plates, 300-meter plates, and basically keep looking, listen to the sky, looking for a patterns, a radio wave patterns cannot be generated by nature. Okay. But when this collapsed, the team actually, or like the organization running this telescopes, they didn't stop this city, correct? SETI. They basically created, they were able to raise more funds, okay, and they built more telescopes, and they continue the operations. That is basically, let us here keep looking for in a patterns of intelligence, like someone like a signals, a radio signals that is does not belong to the nature. Like nature basically has its own patterns of radio waves, okay, through like what's called um, black box radiations, correct? So it has like every heat temperature has its own. And so basically, natural cannot basically generate a radio wave, for example, correct? Like a radio wave. Actually, what we communicate, it's very it has a very interesting patterns actually on it. And if we detect those type of signals, we basically this is indications that is okay. There is intelligent life somewhere. In matter of fact, actually, when they start this Arecibo telescope, they were 100% certain they're gonna find 10,000 Earth-like signal, 10,000 different places in the sky. They were 100%. They were 100% certain that is this is will happen, because it's a matter of probability. If life is a probability, we should look into the sky, okay, and we will find because how we calculate this probability? You just basically say, okay, how many stars like our sun around us, okay, similar to our sun, okay, this number, how many of those actually in the same age, how many of those actually can host the planets, how many of those actually can, how many planets per, and you can do this math, answer these questions, okay, and they come out with estimation, okay, how many star like how many planets like our Earth exist in our nearby stars, and they come out with a number 10,000. So we're 100% certain. And for so many years, they were the telescope was operating. They were not able to detect any signals has a meaning, right? Or basically very strong indicator. Then when this telescope collapsed, okay, and basically they continue with another projects, okay, I think actually they call it I forgot actually how, like they listen, correct? They basically they have a project today actually, they call it breakthrough listen, and that basically they were trying to basically look for one spots, okay, or like many, they were trying to basically look in, listen to the sky in different spots, And the way they do it, they look into the sky and for 5 minutes, then basically shift for another 5 minutes and basically and come back. And they basically try to find signals within a specific range, okay, and see, okay, if it is exists in one location, doesn't exist in the other location, and keep doing that, they can basically say, okay, that basically there is some interesting signal here, and basically let us focus on it. And they published actually recently, like I think actually like a few months ago, actually, they keep been doing that for 10 years, and or like um, very long actually time. And basically so far actually they didn't discover any I think actually the survey not only like inside our Milky Way, they're basically looking at signals from even different uh, galaxies. And unfortunately, they didn't find any interesting signals so far. So that basically, this image, okay, is the one of the very interesting image. Actually, I keep looking at it. Actually, I remember it all the time. That is our, it's Voyager, like in the 70s. Okay, NASA launched this Voyager one. It is basically in the interstellar media. It's basically left the sun, um, gravity. And one of the very interesting images you take is this one. It's almost I cannot see the Earth. Earth is basically, literally, outside our is undetectable. It's just basically a piece of dust somewhere, right? You cannot even um, differentiate. And so far, that is, you're looking into the only form of life we can detect. It's a puzzle. It's a crazy puzzle. But maybe we are the lucky generations of humans that is we can witness, that is we can answer a question because we have the tool that to answer these questions. Are we alone? But until that, that is the only place actually we can host life. That is the only location. That is how precious it is. That's this spot in the whole entire universe so far. We cannot detect any form of life. Our theory says that is we should be life everywhere because this is huge probability that is okay in our neighborhood like us exactly with the same conditions exactly. And how come actually we don't detect any signals? So that's basically is a mystery. Maybe the super intelligent life actually are it basically destroy itself actually as fast as it can. We, the Earth is 4.6 years, but the super intelligent form of life is only like less than a million year, or like maybe even less. Like Homo sapiens actually is much less than that, right? Homo sapiens, so like it's less than that. So it sounds like life is so precious. So anytime actually you look into a butterfly and a flower, or a mosquito biting you biting you, you look into it actually with, or like basically in look into your spouse, look into your neighbors, you are looking in a miracle of life. Something it's very into something extremely rare, and we don't know why it is so rare like that so far. But hopefully in our life we're gonna have an okay into these questions. I'm gonna stop here for now, and I open for questions.
Thank you so much, Salam. That was an incredible presentation. And we have a few questions in the chat that I want to make sure we get to for the recording because people will be coming back. I think Kevin had asked about samples being returned to the Earth from the study probes, and you had talked about the concern of whether they would have hazardous material or not. So I think you addressed that. There's a question about how long will the test mission be slated to run?
Yeah. So it is blend. So most of the missions historically they have a lifetime. Okay. But typically it get extended quite a bit. So TESS basically can maintain orbits for 10 years. So the mission objective was 2 years, but I will not be surprised that it will basically, as long as you can maintain the orbits, okay,
Right.
you can, and you have enough, um, enough fuel basically to do the corrections or like enough, so I think actually you keep it going. And this is like Kibler, for example, actually was also like planned for a few years and extended. It's almost like, for very long time. So it's a typical pattern. Hubble itself, actually, you see, Hubble itself actually is almost like 30 years in operations. It's quite a bit. James Webb actually was planned for only like few years, like two, then basically extended to five, and now they took about 2 years. So I will not be surprised that is okay. Test actually will survive for 10 years if we can get the funds, correct? Like someone has to basically approve the funds. So if they can prove that is okay, the mission still producing good data, they basically will fund it, correct? And they will keep producing good data, correct?
Great.
Mhm.
I'm going to ask you to stop sharing your screen and I'm
Sure.
gonna put people back on the screen. So if folks would like to um, ask questions, um, feel free while we have him. I haven't taken notes before in one of these, and I have pages of notes. So I really have really enjoyed this talk.
Oh,
But does
thank you.
anyone have any questions for Salem? I know myself. I was as you were talking about the missions and the search for life, and when these missions were going to be, the rovers and the landers are going to be getting to their destinations and stuff. I was feeling a sense of pain in my heart because I won't be around for a lot of what's going to be coming, and I want to see it so bad. I want to know what happens.
Let me, science actually is moving faster, extremely faster than what we ever imagined, right? In
Yes.
our lifetime means that is in our parents and grandparents, the knowledge, human knowledge, dramatically changed. From we are Milky Way is the only galaxy into no we are there is hundreds of billions of these galaxies in the sky into quantum mechanics into like Einstein. All this is like a breakthrough in knowledge. It happened very quickly, correct?
Mhm.
And like recently, we have the Large Hadron Colliders in CERN, and for CERN, like in Swiss Alps, and so there is, and James Webb now actually. Science actually, there's so many findings actually happening on a daily basis. So it it's like a groundbreaking knowledge and science. So you never know. You never know. One of those, maybe one time actually someone say, okay, well, you found that's basically like a strong evidence of life. But I think actually to communicate or like to bring samples, it's gonna take some times. Yes, I agree. Or basically to have missions basically to do direct, to look into, like there is, recently announced mission will be launched in 2020, 2040. That is, will be should be able to be capable to do direct imaging to a planet like Earth and very close to stars similar to Earth, So we can basically do direct image. This basically was, we don't have the capability today. James Webb cannot do it. The technology is not invented yet, but it's coming, right? So the advance of knowledge today is moving much, much faster than what it has to be actually 100 years ago. We are living in a very interesting time of human history, right? We are witnessing the starting of AI, the machine learning, and the AI revolutions. We are just starting the scratching the surface. We see that is ChatGPT 4.0. You can chat with it actually as a friend, correct? And can answer any questions you want, and it can basically solve any questions. And trust me, that is only the start. What's coming is crazy, crazier than that. So I will not be surprised that is okay. Something interesting will show up actually in our lifetime, and if not, we are enjoying this new finding coming up, okay, and the new hopes. That is, at least for now, we are enjoying that is okay. We are precious, okay. Maybe in the future, say no, no, there is so many of us actually everywhere, but for now, we are very precious. We have to treat ourselves. We have to treat anything around you as a super rare, precious item, correct? It's basically, it's it sounds like it is much rarer than what you thought. Okay, we believe at the beginning that is okay, life everywhere, but it doesn't show so far, correct? So at least for now, we are egocentric. We believe actually that like we are very rare and we are super rare. The only scary part, that is the only location we can survive. So far we cannot go anywhere else. So either like this is the only house for a human to basically to survive. Either we keep it or we destroy it. If we destroy it, maybe actually the way we basically it is going, we destroy it, and that's why we don't communicate with any intelligent species anywhere, because they destroy each other. Actually, as long as they get the power, they destroy each other. Something like that. We don't know, but it's very interesting to finding so far.
Yes. Does anyone else have any questions or comments? Well, I really, really appreciate your talk. It was very interesting, and I love how you laid the groundwork and built the foundation. Um, I just think it was a great presentation, and
Oh,
I
thank
want
you.
to thank you so much for being a guest here on our
Thank you very
Sol
much.
Speaker Series.
Thank you.
And to everyone else, stay tuned for our next event coming up on the third Thursday of the month in July, which I was so discombobulated with our late start that I didn't get my speaker list out in front of me to tell you who it's going to be. But it'll be another good one, I can guarantee that. So thank you so much, and
Thank you.
everyone have a good night
Okay.
tonight.
Thank you. Thank you very much.
Thank you.
Thank you. Bye bye.
Bye bye.